A single glass plate, no larger than a dinner napkin. It is a photograph of the night sky taken on the evening of October 5th, 1923, and if you were allowed to hold it, which you are not, because it is arguably one of the most important objects in the history of human thought, you would see nothing particularly remarkable. A smear of faint white light against a dark background, a few brighter spots scattered across the frame. In the upper right corner, written in red ink in a tight, precise hand, is a single word followed by an exclamation point. The word is VAR. And that small annotation, that three-letter abbreviation, scrawled by a quiet, pipe-smoking man named Edwin Hubble in the cold dome of the largest telescope then in existence, is the moment the universe as human beings understood it ceased to exist and a new one, staggeringly larger and stranger, took its place. You need to understand what people believed, what they assumed, what they were certain of, because certainty is the thing that science destroys best. In 1923, the universe was small. Not small by everyday standards, of course. The Milky Way was understood to be a vast collection of stars, perhaps 100,000 light-years across, and that was already a number that defeated the imagination. But the Milky Way was everything. It was the entirety of existence. The cloudy patches that astronomers called nebulae, faint, spiral-shaped smudges visible through good telescopes, were thought to be clouds of gas within our own galaxy, formations that might be collapsing to form new stars, interesting but local. The idea that they might be separate galaxies, entire island universes, millions of light years away, had been proposed, debated, and largely dismissed. The astronomer Harlow Shapley, who had just completed his own landmark work measuring the size of the Milky Way, was adamant. There was nothing beyond our galaxy. The Milky Way was the cosmos. And Shapley was brilliant, respected and wrong. Edwin Hubble was not the kind of man who announced revolutions. He was meticulous, formal, somewhat aloof. He had been a boxer, a lawyer, a Rhodes Scholar at Oxford, where he affected a British accent that irritated his American colleagues for the rest of his life. By 1923, he had secured a position at the Mount Wilson Observatory above Pasadena, where the 100-inch Hooker telescope, then the most powerful instrument ever aimed at the sky, peered out from a dome on a mountain that rose above the haze of the Los Angeles basin. Night after night, Hubble pointed that telescope at the Andromeda Nebula, a faint oval smudge in the constellation that bore its name, and took photographs on glass plates, each exposure lasting hours, each plate capturing light that had been traveling for, well, that was precisely the question. On the night of October 5, he found what he was looking for. A single star in the Andromeda Nebula that was varying in brightness. Not a nova, not an explosion, but a Cepheid variable, a type of star that pulses with a regular rhythm, brightening and dimming like a slow heartbeat. And Cepheid variables were special because a woman named Henrietta Swan Leavitt had discovered years earlier that there was a precise relationship between how fast a Cepheid pulsed and how bright it actually was. If you knew the period, you knew the true brightness. And if you knew the true brightness and compared it to how bright the star appeared from Earth, you could calculate the distance with startling precision. It was a cosmic ruler, and Hubble had just found one in Andromeda. He did the math. The answer was roughly 900,000 light-years. The modern measurement is about 2.5 million. Hubble's calibration was off, but the essential point was beyond dispute. Andromeda was far, far beyond the edge of the Milky Way. It was not a cloud of gas within our galaxy. It was a galaxy of its own, a collection of billions of stars, and it was outside. The universe had just expanded by a factor that no one was prepared for, and that word scrawled in red ink, VAR, was the first crack in a wall that would never be rebuilt. Hubble published his findings in early 1925. The response was not immediate fanfare. Science rarely works that way. There were questions, objections, requests for more data. Shapley, upon receiving Hubble's letter describing the result, reportedly said it had destroyed his universe. He was not being dramatic. It had, within a few years, as Hubble identified Cepheids in other nebulae. The picture became inescapable. The Milky Way was not the universe. It was one galaxy among what appeared to be millions, each one a vast city of stars separated by gulfs of empty space so enormous that light itself needed millions of years to cross them. The night sky, which had seemed like a ceiling, turned out to be a window, and beyond that window was something that no human mind had ever seriously contemplated. A universe of structure and scale that made the entire Earth, the entire solar system, the entire galaxy into something almost vanishingly small. And yet, even as astronomers absorbed this shock, the universe was preparing another one. If you had been standing beside Hubble in the late 1920s, watching him work through his photographic plates night after night, you might have noticed something odd about the light coming from those distant galaxies. Light, as it travels through space, carries information not just about brightness but about motion. When an object moves away from you, its light stretches slightly, shifting toward the red end of the spectrum, the same principle that makes a siren's pitch drop as an ambulance drives away. This is called redshift, and it was not a new concept. What was new was the pattern Hubble was finding. Nearly every galaxy he measured was redshifted. They were all moving away, and the farther away a galaxy was, the faster it appeared to be receding. This was not what anyone expected. The prevailing assumption held by Einstein himself, who had built it into his equations of general relativity as a mathematical constant, was that the universe was static, eternal, unchanging, a fixed stage on which the drama of physics played out. Einstein had even added a term to his equations, the cosmological constant, specifically to prevent them from predicting what Hubble was now observing. The equations of general relativity naturally described a universe that was either expanding or contracting, and Einstein had considered this so absurd, so obviously wrong, that he had inserted a fudge factor to keep things still. He would later call it the greatest blunder of his life, though the real irony is that the cosmological constant would return decades later in a form even he could not have imagined, but that story will have to wait. Hubble's discovery, published in 1929, was stated with the understated precision that characterized his work. The velocity of recession of distant galaxies was proportional to their distance. The farther away, the faster they fled. This relationship became known as Hubble's law, and its implication was staggering. The universe was expanding. Not the galaxies moving through space like shrapnel from an explosion, but space itself stretching, carrying the galaxies with it like raisins in rising bread dough, every point in the universe moving away from every other point, not because anything was pushing them, but because the fabric of reality between them was growing. Run the expansion backward in your mind. If everything is moving apart now, then yesterday everything was closer together. 1,000,000 years ago, closer still. 1,000,000,000 years ago, the universe was denser, hotter, compressed into a smaller volume. Keep rewinding 10 billion years, 12 billion, 13, and at some point, all the matter and energy and space in the observable universe was compressed into a state of unimaginable density and temperature, a singularity, a point from which everything began. The idea was first proposed in a serious mathematical framework by a Belgian priest and physicist named Georges Lemaitre, who called it the primeval atom. It was given its famous name, the Big Bang, as a term of mockery by the British astronomer Fred Hoyle, who thought the whole idea was ridiculous. Hoyle preferred an eternal, steady-state universe, one that had always existed and always would. He coined the phrase Big Bang during a BBC radio broadcast in 1949, intending it to sound silly. The name stuck. The mockery did not. For decades, the Big Bang remained a hypothesis, elegant, mathematically consistent, but unproven. Its supporters and detractors argued fiercely, and the debate might have continued for generations if not for a piece of equipment that was never designed to look at the sky and two men who were not looking for the beginning of the universe. Picture a large horn-shaped antenna in Holmdel, New Jersey in the spring of 1964. It looks less like a telescope than like a gigantic ear trumpet, 20 feet across. Originally built by Bell Telephone Laboratories to detect signals bounced off communication satellites. Two young radio astronomers, Arno Penzias and Robert Wilson, had been assigned to calibrate this antenna for radio astronomy work, and they had a problem. No matter where they pointed the antenna, north, south, east, west, toward the Milky Way, or away from it, they detected a faint, persistent hiss of microwave radiation. It was everywhere. It was uniform. It would not go away. They checked everything. They rebuilt connections, tested circuits, eliminated every source of interference they could think of. They even climbed inside the horn and scraped out the droppings of pigeons that had been nesting there on the theory that pigeon excrement might somehow be producing a microwave signal. It was not the pigeons. The signal remained a faint, constant glow coming from every direction in the sky, corresponding to a temperature of about 2.7 degrees above absolute zero. What Penzias and Wilson had found, and what they did not initially realize, was the afterglow of creation itself. The cosmic microwave background radiation, the CMB, is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, at the moment when the universe had cooled enough for atoms to form and for photons to travel freely through space for the first time. That light has been traveling ever since, stretching and cooling as the universe expanded, and it fills every cubic centimeter of space. If you tune an old analog television to a channel with no signal, about 1% of the static you see on the screen is this light, the remnant radiation of the moment the universe became transparent, arriving at your antenna 13.8 billion years after it began its journey. Penzias and Wilson won the Nobel Prize. The Big Bang went from hypothesis to established science, and the universe acquired something it had never had in the entire history of human thought, a birthday, an age, a beginning. Not infinitely old, not eternally unchanging, but born in fire and expanding ever since, cooling and thinning and forming structures, galaxies, stars, planets, eventually atoms complex enough to ask questions about their own origin. The discovery of the CMB did more than confirm the Big Bang. It provided a map, not just any map, perhaps the most important map ever made. When satellites were eventually launched to measure the CMB with extraordinary precision, first COBE in 1989, then WMAP in 2001, and finally Planck in 2009, they revealed something astonishing. The radiation was not perfectly uniform. There were tiny fluctuations in temperature, variations of about 1 part in 100,000 ripples in the fabric of the early universe, so slight that they amounted to differences of millionths of a degree, and those ripples were the seeds of everything. Where the radiation was slightly warmer, matter was slightly denser. Those denser regions exerted slightly more gravitational pull, attracting more matter, growing over billions of years into the vast filaments and walls of galaxies that make up the large-scale structure of the universe today. Where the radiation was slightly cooler, matter was slightly less dense, and those regions became the vast cosmic voids, bubbles of near emptiness, hundreds of millions of light years across. The pattern of hot and cold spots in the CMB is, quite literally, the blueprint of the cosmos. Every galaxy, every star, every planet, every person reading these words exists because of a fluctuation in density that occurred when the universe was smaller than a grapefruit. The CMB map also told us the age of the universe with startling precision, 13.797 billion years, plus or minus about 20 million. It told us the geometry of space flat, or very nearly so, meaning that parallel lines remain parallel even across cosmic distances. It told us the composition of everything, about 5% ordinary matter, the atoms that make up stars and planets and human bodies, about 27% something called dark matter, and about 68% something even stranger called dark energy. If those last two numbers unsettled you, they mean that everything humanity has ever seen, touched, measured or built is made of a type of matter that accounts for less than 1/20th of the total content of the universe. The rest is invisible, undetectable by any direct means and only partially understood. We are, in a very real sense, a rounding error in the cosmic inventory. The story of dark matter begins not with a theorist at a blackboard, but with a stubborn astronomer staring at numbers that refuse to make sense. Fritz Zwicky was Swiss, brilliant, combative, and widely disliked by his colleagues, whom he cheerfully referred to as spherical bastards, because he explained they were bastards no matter which direction you looked at them. In the 1930s, Zwicky was studying the Coma cluster, a dense collection of over 1,000 galaxies about 320 million light-years from Earth. He measured the velocities of the galaxies within the cluster and found something disturbing. They were moving too fast, far too fast. Based on the visible mass of the cluster, the total light output of all its galaxies, which told you how many stars were present, there was not nearly enough gravitational pull to hold the cluster together. The galaxies should have been flying apart, scattering into the void like sparks from a fire, but they were not flying apart. The cluster was intact, had been intact for billions of years, and was clearly being held together by gravity. So where was the mass producing that gravity? Zwicky proposed that the cluster contained vast amounts of invisible matter, material that exerted gravitational force but emitted no light. He called it dunkle materie, dark matter, and estimated that the cluster must contain about 400 times more dark matter than visible matter. His colleagues largely ignored him. Zwicky was abrasive, his estimates seemed extreme, and the instruments of the 1930s were not precise enough to rule out measurement errors. The idea gathered dust for 40 years. Then came Vera Rubin. In the 1970s, Vera Rubin was studying the rotation of spiral galaxies, measuring how fast stars at different distances from the galactic center were orbiting. According to Newton's laws and everything astronomers understood about gravity, stars far from the center should orbit more slowly than stars close in, just as the outer planets of our solar system orbit more slowly than the inner ones. The mass was concentrated at the center, so the gravitational pull weakened with distance, and the orbital speeds should decline accordingly. This is called a Keplerian decline, and it is one of the most basic predictions of gravitational physics. Rubin's galaxies did not show a Keplerian decline. The rotation curves were flat. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center, sometimes faster. This was not possible unless there was far more mass in the outer regions of the galaxy than the visible stars accounted for. Unless, in other words, each galaxy was embedded in a vast halo of invisible matter, a sphere of something that could not be seen or detected directly, but whose gravitational influence was undeniable. Rubin measured galaxy after galaxy. The result was always the same. Every spiral galaxy she studied showed the same flat rotation curve, the same impossible velocities, the same inescapable conclusion: most of the matter in the universe was dark. It was not stars, it was not gas, it was not dust, it was not black holes, not planets, not any form of ordinary matter that had simply failed to ignite. Later observations would confirm this. The CMB measurements, gravitational lensing studies, computer simulations of cosmic structure formation, all pointing to the same answer. Dark matter is real, it is abundant, it shaped the universe, and after nearly a century of searching, no one has yet identified what it actually is. The leading candidates are hypothetical particles, WIMPs, weakly interacting massive particles, or axions, or some other exotic entity predicted by extensions of the standard model of particle physics. Enormous detectors have been built deep underground, in abandoned mines and beneath mountains, shielded from cosmic rays, waiting patiently for a dark matter particle to collide with an atom of xenon or germanium and produce a faint telltale flash. So far, nothing. The detectors grow more sensitive, the searches more comprehensive, the null results more puzzling. Dark matter holds the galaxies together, sculpts the cosmic web, and constitutes more than a quarter of everything that exists, and it remains one of the deepest unsolved mysteries in all of science. If you find the idea of an invisible substance permeating the universe unsettling, the story of dark energy will not comfort you. In 1998, two independent teams of astronomers set out to measure something that everyone assumed they already knew the answer to. The universe was expanding. Hubble had established that 7 decades earlier, and the expansion was presumably slowing down. Gravity, after all, pulls matter together. Every galaxy attracts every other galaxy over time. This mutual attraction should act as a brake, gradually decelerating the expansion the way friction slows a rolling ball. The question was not whether the expansion was slowing, but how quickly, and whether it would eventually stop or even reverse, collapsing the universe back into a singularity in a kind of mirror image of the Big Bang, the Big Crunch, to measure the deceleration. Both teams used a particular type of exploding star called a type Ia supernova. These supernovae occur when a white dwarf star, the dense exhausted remnant of a star like our Sun, accumulates enough material from a companion star to cross a critical mass threshold and detonate in a thermonuclear explosion so bright that it can outshine an entire galaxy for weeks. The beautiful thing about type Ia supernovae is that they all explode at roughly the same mass, which means they all reach roughly the same peak brightness. They are standard candles. If you know how bright something actually is and you measure how bright it appears, you can calculate how far away it is. And the redshift of the host galaxy tells you how fast it is receding. Plot distance against recession speed for dozens of distant supernovae, and you can trace the expansion history of the universe. Both teams expected to find deceleration. Both teams found the opposite. The distant supernovae were dimmer than they should have been, farther away than they should have been, which meant the expansion of the universe was not slowing down. It was speeding up. The universe was accelerating. This was, to use a word that physicists rarely employ, shocking. It meant that something was overpowering gravity on the largest scales, pushing space apart faster and faster. Not a force in any conventional sense, not a push from somewhere, but a property of space itself, an energy inherent in the vacuum, a pressure that increases as more space is created, driving the expansion to accelerate without limit. This something was given the name dark energy, and it accounts for roughly 68% of the total energy content of the universe. No one knows what dark energy is. It may be Einstein's cosmological constant resurrected, the very term he added to his equations and then regretted, now reinterpreted not as a mistake but as a genuine feature of space-time. It may be something dynamic, a field that changes over time, sometimes called quintessence. It may be a signal that our understanding of gravity itself is incomplete, that general relativity, for all its triumphs, breaks down at the largest scales. What is clear is that the universe is not just expanding but accelerating in its expansion, and that this acceleration will continue, and that in the extremely distant future, hundreds of billions of years from now, every galaxy beyond our local group will have receded so far and so fast that its light will never reach us again. The observable universe will shrink, the night sky will go dark. The stars of distant galaxies will pass beyond a horizon from which no signal can ever return, and the universe will become, for any observer within it, a smaller and lonelier place, but that is the far future, and the near past has been strange enough. Consider this: for almost the entire history of astronomy, from the Babylonians to the 1990s, no human being knew for certain whether any star other than our Sun had planets orbiting it. The idea was ancient. Epicurus suggested it in the 3rd century BC, and Giordano Bruno was burned at the stake in 1600, in part for insisting that the stars were suns with their own worlds, but it remained speculation. Planets around other stars were too small, too faint, too close to the blinding glare of their parent stars to be detected by any instrument ever built. The solar system might have been unique. Earth might have been the only planet in the universe. There was no way to know. The first confirmed detection of a planet orbiting a sun-like star came in 1995 from an observatory in southeastern France. Michel Maire and Didier Queloz were using a spectrograph attached to a telescope at the Haute-Provence Observatory, measuring the radial velocity of a star called 51 Pegasi, an unremarkable yellow star in the constellation Pegasus, about 50 light-years from Earth. They noticed a tiny rhythmic wobble in the star's motion, a back and forth shift of a few dozen meters per second, repeating every 4.2 days. The only explanation was that something massive was orbiting the star, tugging it gravitationally, causing it to rock slightly on its axis, a planet. But not a planet anyone had expected. The orbital period of 4.2 days meant the planet was unthinkably close to its star, far closer than Mercury is to our Sun, and the amount of wobble meant the planet was roughly half the mass of Jupiter. A giant planet, a gas ball larger than any rocky world, orbiting so close to its star that its surface temperature would exceed 1,000 degrees. This was not in any textbook. No model of planet formation predicted such a thing. Gas giants were supposed to form far from their stars, in the cold outer reaches of planetary systems where volatile gases could condense. Finding one in a scorching 4-day orbit was like finding a snowman in a furnace. The discovery of 51 Pegasi b, later named Dimidium, did not just add one planet to the catalogue. It broke the assumption that all solar systems would look like ours. The universe, it turned out, was far more creative than human theorists had given it credit for. Hot Jupiters, as this new class of planet came to be called, were everywhere, and they were only the beginning. The real revolution came with the Kepler Space Telescope, launched by NASA in 2009 with a single focused mission: stare at one patch of sky about the size of your outstretched hand and watch 150,000 stars simultaneously for years, looking for the faintest possible dimming, a tiny dip in brightness that would occur when a planet passed in front of its star, blocking a fraction of a percent of the star's light. This is the transit method, and it requires extraordinary precision. The dimming caused by an Earth-sized planet crossing a Sun-like star is about 0.01%, like detecting a firefly passing in front of a searchlight from 1,000 miles away. Kepler found thousands of them. In just 4 years of primary observations, it detected over 2,600 confirmed exoplanets and thousands more candidates, transforming the search for other worlds from a niche pursuit into one of the most data-rich fields in all of astronomy. And the diversity was staggering. Planets the size of Neptune in tight orbits, planets smaller than Earth, planets orbiting 2 stars simultaneously, like Tatooine in the Star Wars films, with double sunsets that are not fiction but measured reality. Planets in the habitable zone of their stars, that narrow band of orbital distance where temperatures might allow liquid water to exist on the surface, the zone that astrobiologists, with characteristic understatement, call the Goldilocks zone. Not too hot, not too cold. The statistical conclusion was overwhelming based on Kepler's data. Astronomers estimate that there are more planets in the Milky Way than there are stars, at least one planet on average for every star. Some estimates put the number of rocky, Earth-sized planets in the habitable zones of their stars at around 11 billion in our galaxy alone. 11 billion potential Earths orbiting 11 billion suns in one galaxy among trillions. The question, are we alone, did not get an answer from Kepler, but it got a new context, and the context is dizzying. As telescopes grew more powerful and techniques more refined, astronomers began to do something that would have seemed like pure fantasy a generation earlier. They began to analyze the atmospheres of these distant worlds. When a planet transits its star, a tiny sliver of starlight passes through the planet's atmosphere on its way to our telescopes. Different molecules absorb different wavelengths of light, leaving characteristic fingerprints in the spectrum. Water vapor, carbon dioxide, methane, sodium, potassium, each leaves its own signature, and instruments sensitive enough can read those signatures across distances of dozens or hundreds of light years. The James Webb Space Telescope launched on Christmas Day 2021 and positioned at a point in space called L2, about 1.5 million kilometers from Earth, was designed in part to do exactly this. Its 6.5-meter gold-plated mirror, folded like origami for the rocket ride and then unfolded in space with a precision that left its engineers sleepless for weeks, collects infrared light with a sensitivity that makes Hubble look like a pair of binoculars. In its first year of operation, Webb detected carbon dioxide in the atmosphere of an exoplanet called WASP-39b, the first unambiguous detection of CO2 in an exoplanet atmosphere. It found evidence of silicate clouds, clouds made of vaporized rock on a brown dwarf. It peered into the atmospheres of planets in the TRAPPIST-1 system, 7 roughly Earth-sized worlds orbiting a cool red dwarf star just 40 light-years away, and began the slow, painstaking work of determining whether any of them hold the chemical signatures that might indicate the presence of life. We have not found that signature yet. No detection of oxygen together with methane, the combination that on Earth is produced and maintained almost exclusively by biological processes. No unambiguous biosignature from any world beyond our own. But the tools to make that detection now exist. The targets have been identified, and the search is underway with an intensity and precision that the previous generation of astronomers could barely have dreamed of. Whether the answer comes in 5 years or 50, whether it comes from a rocky planet around a nearby star or from a moon in our own solar system, and there are reasons to look very carefully at those moons, the question is no longer theoretical. It is observational. It is a matter of data, not philosophy. Speaking of moons in our own solar system, something extraordinary was discovered hiding beneath the surface of worlds that from the outside look like frozen, dead places. Europa is a moon of Jupiter, slightly smaller than Earth's moon, covered in a shell of ice that is among the smoothest surfaces in the solar system. From a distance, it looks like a cracked egg, a pale cream-colored sphere crisscrossed with reddish-brown lines that stretch for thousands of kilometers, giving it an eerie, veined appearance. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, found something beneath that ice shell that changed everything we thought we knew about, where life might be possible. The surface ice was not sitting on solid rock. It was floating on an ocean, a global saltwater ocean, estimated to contain about twice as much liquid water as all of Earth's oceans combined. The tidal flexing of Jupiter's enormous gravity, the same force that makes Europa's orbit slightly elliptical, generates enough internal heat to keep this ocean liquid, despite surface temperatures of minus 160 degrees Celsius. In places, the ice shell appears to be only a few kilometers thick, and features on the surface suggest that water from the ocean below has erupted through cracks in the ice, leaving behind the reddish mineral deposits that streak the surface. An ocean of liquid salt water, kept warm by gravitational energy, shielded from radiation by a shell of ice. It is, by some measures, the most promising environment for extraterrestrial life in the solar system. Not life as we might romantically imagine it, not cities, not civilizations, but microbial life, the kind of single-celled organisms that thrive in the most extreme environments on Earth. In the deep ocean trenches of our own planet, far from sunlight, near hydrothermal vents where superheated water laden with minerals erupts from the sea floor, entire ecosystems flourish, powered not by photosynthesis but by chemosynthesis, living on chemical energy from the Earth itself. If such vents exist on Europa's ocean floor, and the conditions for them appear to be met, then life might exist there right now, in our own solar system, swimming in darkness beneath miles of ice, completely independent of sunlight, utterly unaware of the universe beyond its ceiling, and Europa is not alone. Enceladus, a tiny moon of Saturn, barely 500 kilometers across, small enough to fit inside the borders of Spain, is doing something that no one expected when the Cassini spacecraft arrived at Saturn in 2004. Geysers, enormous plumes of water vapor and ice particles erupting from fractures near the moon's south pole, shooting hundreds of kilometers into space. Cassini flew through those plumes multiple times, sampling their contents, and found water, salt, silica nanoparticles, a sign of hydrothermal activity, and most tantalizingly molecular hydrogen, which on Earth is produced by the interaction of hot water with rock and is used as an energy source by certain microorganisms. Enceladus too has a subsurface ocean heated by tidal forces, and it is literally shooting samples of that ocean into space for us to analyze. A future mission could fly through those plumes with the right instruments and potentially detect the chemical signatures of life without ever having to land. The universe, it seems, is far more generous with liquid water than anyone suspected a few decades ago. Subsurface oceans may exist beneath the ice of Ganymede, Callisto, Titan, and perhaps even Pluto. The conditions for life, liquid water, chemical energy, organic molecules, are not rare cosmic accidents confined to a single blue planet in a single solar system. They may be common, distributed widely across the moons of giant planets throughout the galaxy. The habitable zone, that narrow ring around a star where temperatures are right for surface water, may be only a small part of the story. Life might not need a star's warmth at all. It might only need gravity, water, and chemistry. And those ingredients are everywhere. But let us return to the stars themselves, because one of the strangest objects in the universe was discovered by accident, by a graduate student who almost dismissed it as interference. And it forced physicists to confront a form of matter so extreme that it defies everyday intuition. In 1967, Jocelyn Bell Burnell was a doctoral student at Cambridge, helping to build and operate a radio telescope designed to study quasars, distant, extraordinarily bright objects that were themselves a recent and puzzling discovery. The telescope was enormous but crude by modern standards, an array of wooden posts and wires strung across a field the size of 57 tennis courts. Bell's job was to analyze the output, which came as pen traces on hundreds of feet of chart paper each day. It was tedious, meticulous work, the kind of work that was routinely assigned to graduate students, and that required a particular kind of patience and attention. On the chart paper for November 28, 1967, Bell noticed something odd, a brief repeating pulse of radio energy occurring with extraordinary regularity once every 1.337 seconds, precise to fractions of a millisecond. Nothing natural should pulse with that kind of clockwork regularity. Stars flicker, quasars vary, but nothing repeats with the metronomic precision of a ticking clock. The initial response from Bell and her supervisor, Anthony Hewish, was a mixture of bafflement and half-serious speculation. They labeled the source LGM1 for Little Green Men, acknowledging the tongue-in-cheek possibility that such a regular signal might be artificial. It wasn't, of course. When Bell found a second pulsing source in a completely different part of the sky, the LGM hypothesis evaporated. Whatever these objects were, they were natural, and they were not rare. What Bell had discovered was a pulsar, a neutron star, spinning rapidly, emitting beams of radio energy from its magnetic poles like a cosmic lighthouse. And a neutron star is one of the most astonishing objects in the known universe. It is the collapsed core of a massive star that has exhausted its nuclear fuel, exploded as a supernova, and had its core compressed by the force of the explosion into a ball of matter so dense that a teaspoon of it would weigh about 1 billion tons. The entire star, with a mass greater than our Sun, is crushed into a sphere roughly 20 kilometers across, about the size of a city. The atoms themselves are destroyed. The electrons are forced into the protons, creating a solid mass of neutrons packed together as tightly as physics allows. The surface gravity is about 200 billion times stronger than Earth's. If you dropped a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with the energy of a small nuclear weapon. The discovery earned Hewish the Nobel Prize. Bell, the person who actually found the pulsars, was not included, a decision that has been debated and criticized ever since. Bell herself handled the omission with remarkable grace, noting that it was not unusual at the time for students to be overlooked, and that the award recognized the project and the telescope rather than the specific observation. She later received numerous other honors, and in 2018 was awarded the Special Breakthrough Prize in Fundamental Physics, $3 million, which she donated in its entirety to fund scholarships for underrepresented students in physics. The universe, at least in this case, eventually corrected itself. Pulsars turned out to be far more than curiosities. Their extraordinary rotational stability made them the most precise clocks in the universe. Some millisecond pulsars keep time more accurately than atomic clocks. They became tools for testing general relativity in extreme conditions. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, 2 neutron stars orbiting each other, and showed that the system was losing energy at exactly the rate predicted by Einstein's theory if it was radiating gravitational waves. This was the first indirect evidence for gravitational waves, and it earned them the Nobel Prize in 1993. The waves themselves would not be directly detected for another 2 decades, and that detection would be one of the most extraordinary technological achievements in human history. Imagine you could somehow sense the fabric of space itself, not the objects in it, not the stars or planets or photons, but space, the medium through which everything moves and exists. Einstein's general relativity describes this fabric as dynamic, capable of curving, stretching, and vibrating. When massive objects accelerate, when 2 black holes spiral toward each other and merge, when neutron stars collide, they create ripples in space-time that propagate outward at the speed of light, stretching and compressing space as they pass. These are gravitational waves predicted by Einstein in 1916, and for nearly a century they were considered a theoretical curiosity, real perhaps, but so fantastically faint that no instrument could ever hope to detect them. The Laser Interferometer Gravitational Wave Observatory, LIGO, was built to do the impossible. It consists of 2 facilities, one in Hanford, Washington, and one in Livingston, Louisiana, separated by 3,000 kilometers, each containing an L-shaped vacuum chamber 4 kilometers long on each arm. A laser beam is split, sent down each arm, bounced off mirrors at the far end, and recombined. If a gravitational wave passes through the detector, it stretches one arm and compresses the other by an almost inconceivably small amount, less than 1/10,000th the diameter of a proton. LIGO was designed to measure this, and for years it measured nothing, and the skeptics grew louder, and the funding was questioned, and the project persisted. On September 14, 2015, at 5:51 a.m. Eastern Time, both LIGO detectors registered a signal, a chirp, a rising tone lasting less than a second, sweeping upward in frequency before cutting off abruptly. The waveform matched, with almost perfect precision, the theoretical prediction for two black holes spiraling together and merging. Each black hole was roughly 30 times the mass of the Sun. They had been orbiting each other, drawing closer, spiraling faster, until in the final fraction of a second they merged into a single black hole of about 62 solar masses. The missing 3 solar masses had been converted into energy, pure gravitational wave energy, radiated outward in that brief chirp. In that fraction of a second, the merging black holes emitted more energy than all the stars in the observable universe combined. And the signal, after traveling 1.3 billion years across space, arrived at Earth and stretched LIGO's 4-kilometer arms by a distance smaller than the nucleus of an atom. The announcement made in February 2016 was one of those rare moments when the entire scientific community paused. It was not just a detection, it was the opening of a new window on the universe, a new sense, a new way of perceiving reality. For all of human history, we had studied the universe through light, visible light, radio waves, X-rays, infrared, gamma rays, all forms of electromagnetic radiation. Gravitational waves are something fundamentally different. They are not light, they are vibrations in the structure of space itself. Detecting them was like being deaf your entire life and suddenly hearing for the first time. And the first sound was 2 black holes colliding in the dark, 1.3 billion light years away, in a galaxy that no one had ever looked at or thought about. 2 years later, LIGO and its European counterpart Virgo detected something even more spectacular, 2 neutron stars colliding. This event, designated GW170817, was different because neutron star mergers produce not only gravitational waves but also light, enormous amounts of it, across the entire electromagnetic spectrum. Within seconds of the gravitational wave detection, the Fermi Gamma Ray Telescope detected a burst of gamma rays from the same region of sky. Within hours, telescopes around the world were pointed at the source, watching a kilonova, the explosion produced when 2 neutron stars merge, unfold in real time. The observations confirmed something that had been theorized for decades, that the heaviest elements in the universe, gold, platinum, uranium, are forged in the collision of neutron stars. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a nuclear reactor, all of it was created in the catastrophic merger of dead stars scattered into space by the explosion, eventually incorporated into the clouds of gas and dust from which new solar systems form. You are quite literally wearing the debris of a cosmic cataclysm. This brings us to one of the most profound realizations of the last century, one that connects astrophysics to chemistry to biology in a way that would have astonished anyone living before the 1950s. The atoms in your body were not always in your body, they were not always on Earth, they were not always in the solar system. The hydrogen in the water in your cells is primordial, forged in the first few minutes after the Big Bang, when the universe was a hot, dense soup of protons and neutrons, and the nuclear reactions that fused them were the same processes that power hydrogen bombs. That hydrogen has been around for 13.8 billion years, drifting through interstellar space, collapsing into stars, being released again, and eventually finding its way into the molecular cloud that collapsed to form the Sun and its planets 4.6 billion years ago. Now consider the objects that are perhaps the strangest endpoints of stellar evolution, the things that push general relativity to its mathematical limits, and then beyond, the objects that even Einstein was not sure could exist in reality. Black holes were first proposed as a mathematical consequence of general relativity, not as physical objects anyone expected to find. In 1916, within months of Einstein publishing his field equations, a German physicist named Karl Schwarzschild, serving on the Russian front in World War I, suffering from a painful autoimmune disease that would kill him within the year, found an exact solution to the equations that described the space-time around a perfectly spherical, non-rotating mass. The solution had a disturbing feature at a certain radius, which came to be called the Schwarzschild radius. The equations produced a singularity, a point where the mathematics broke down, where quantities became infinite, where the known laws of physics ceased to apply for a mass the size of the Sun. This radius was about 3 kilometers. If you could compress the Sun to a ball 3 kilometers across, space-time around it would curve so steeply that nothing, not light, not matter, not information of any kind, could escape from within that radius. The boundary was called the event horizon, and what lay beyond it was, mathematically at least, a hole in the fabric of reality. For decades, most physicists regarded black holes as mathematical curiosities, solutions to the equations that probably did not correspond to anything real. The idea that matter could actually be compressed to such densities seemed absurd. Einstein himself published a paper in 1939 arguing that black holes could not form in nature. He was once again wrong. The evidence accumulated slowly. Then, all at once, in 1964, astronomers detected an intense source of X-rays in the constellation Cygnus X1 that appeared to be a compact object pulling matter from a companion star. The matter, spiraling inward at enormous speeds, heated to millions of degrees and emitted X-rays before crossing the event horizon. The mass of the compact object was estimated at about 15 times the mass of the Sun, far too heavy to be a neutron star, which has a maximum mass of about 2 to 3 solar masses. If it was not a neutron star and it was not emitting light of its own, and it had a mass of 15 suns, then there was only one thing it could be. Throughout the following decades, evidence mounted from every direction. Supermassive black holes, millions to billions of times the mass of the Sun, were found at the centers of galaxies, including our own. The Milky Way's central black hole, Sagittarius A, has a mass of about 4 million suns and lurks behind vast clouds of interstellar dust at the galactic center, 26,000 light-years from Earth. Stars near the galactic center were tracked for years as they orbited this invisible mass, their paths tracing elegant ellipses around a point that emitted no light, confirming its nature beyond any reasonable doubt. Andrea Ghez and Reinhard Genzel shared the Nobel Prize in 2020 for this work, along with Roger Penrose for his theoretical contributions to the understanding of black hole formation. And then in April 2019 the world saw one. The Event Horizon Telescope is not a single telescope. It is a network of 8 radio observatories on 4 continents, from Hawaii to Spain to the South Pole, linked together using a technique called very long baseline interferometry to create, in effect, a telescope the size of the Earth. The resolution is extraordinary, equivalent to being able to read a newspaper in New York from a cafe in Paris. This planet-sized virtual telescope was aimed at the supermassive black hole at the center of the galaxy M87, a giant elliptical galaxy about 55 million light-years away in the constellation Virgo. And over several nights in April 2017, it collected data, petabytes of data, so much data that it was faster to physically ship the hard drives by airplane than to transmit them over the internet. The image, released 2 years later after painstaking analysis, showed exactly what general relativity predicted: a bright ring of superheated gas and plasma, swirling around a dark central shadow, the silhouette of the event horizon, the boundary beyond which light cannot escape. The black hole at M87 center has a mass of 6.5 billion suns. The event horizon is larger than the orbit of Neptune. The ring of light is matter spiraling inward at close to the speed of light, heated to billions of degrees, glowing ferociously in its final moments before crossing the point of no return. The image is blurry, pixelated, and represents perhaps the single most impressive achievement in the history of observational astronomy. It is a photograph of the unseeable, an image of absence, of the place where space-time curves so sharply that the universe effectively swallows itself. A few years later, in 2022, the Event Horizon Telescope released an image of Sagittarius A, the black hole at the center of our own galaxy. Smaller, closer, harder to image because the surrounding gas changes on timescales of minutes rather than the days-long stability of M87's giant. It nonetheless appeared as the same glowing ring with a dark center. Two black holes, two galaxies, one theory, and the theory matched reality with humbling precision. But black holes are not just destroyers. They are, in a strange and still poorly understood way, architects. Nearly every large galaxy appears to harbor a supermassive black hole at its center, and the mass of that black hole is closely correlated with the mass and properties of the galaxy itself. The bigger the galaxy, the bigger the black hole. The faster the stars in the galaxy's central bulge move, the more massive the central black hole. This correlation is too tight to be a coincidence. It suggests that galaxies and their central black holes grow together, that the black hole somehow regulates the galaxy's development, perhaps by periodically erupting in enormous jets of energy that heat the surrounding gas and prevent it from cooling and forming too many new stars, acting as a thermostat for an entire galaxy. The details of this coevolution are one of the most active areas of research in modern astrophysics, and the James Webb Space Telescope has already begun to complicate the picture by finding surprisingly massive black holes in the very early universe, black holes that seem too large to have formed through the slow accumulation of matter. How they grew so big so fast is a question that does not yet have a satisfying answer. The early universe, in fact, has been full of surprises. One of the most unexpected came from a project that started as a gamble and became one of the most famous images in the history of science. In December 1995, Robert Williams, the director of the Space Telescope Science Institute, made a decision that many of his colleagues thought was foolish. He pointed the Hubble Space Telescope at a patch of sky that appeared to be completely empty, a tiny region in the constellation Ursa Major, about the size of a grain of sand held at arm's length, chosen specifically because it contained no bright stars, no known galaxies, no objects of interest, nothing. And he kept the telescope pointed there for 10 consecutive days, accumulating 342 separate exposures, each one soaking up the faintest traces of light from the most distant objects in the universe. The resulting image, the Hubble Deep Field, is one of the most profound photographs ever taken in that seemingly empty speck of sky, smaller than 1/100th of a square degree. The Hubble revealed nearly 3,000 galaxies, not stars galaxies, each one containing billions of stars, scattered across billions of light years of depth, some of them so distant that their light had been traveling for more than 10 billion years. Galaxies in every stage of development, bright spirals, chaotic irregulars, faint red smudges that were among the most distant objects ever seen. The empty patch of sky was not empty at all. It was teeming with structure, filled to overflowing with galaxies that had been invisible until someone had the audacity and the authority to stare at nothing for 10 days. The deep field changed how astronomers thought about the universe. It provided the first truly direct evidence that galaxies were abundant in the early universe, that the process of galaxy formation began much earlier than many models predicted, and that the universe was, in a word, full. Subsequent deep field observations, the Hubble Ultra Deep Field in 2004, which looked even longer and deeper, and the James Webb Space Telescope's deep field images beginning in 2022, pushed the frontier further, revealing galaxies that existed when the universe was only a few 100 million years old, galaxies that should not have had time to form, galaxies that challenge our models of how quickly matter can organize itself under gravity. The total number of galaxies in the observable universe is estimated at around 2 trillion, 2,000 billion, each containing between a few million and several hundred billion stars. The total number of stars in the observable universe is estimated at something like 200 billion trillion, a 2 followed by 23 zeros. This number exceeds the number of grains of sand on every beach and desert on Earth. It exceeds the number of human heartbeats that have ever occurred in the entire history of the species. And each of those stars, on average, has at least one planet. The universe is not merely large, it is incomprehensibly, ludicrously, absurdly, magnificently large, and the fact that we can say anything meaningful about it at all, that we can measure its age, map its structure, predict its behavior, photograph its darkest objects, is a testament to something remarkable about the particular arrangement of atoms that constitutes the human brain, and the structure is not random. If you could somehow pull back far enough to see the large-scale arrangement of matter in the universe, if you could map every galaxy in 3 dimensions across billions of light years, you would see something that looks remarkably like a web. Filaments of galaxies stretching across hundreds of millions of light years, like the strands of a spider's web or the neural networks of a brain, with dense knots at the intersections where galaxy clusters congregate and vast empty voids between the filaments where almost nothing exists. This is the cosmic web, and its existence was predicted by computer simulations before it was observed. Dark matter provides the scaffolding, the invisible framework of gravitational potential around which ordinary matter collects. Gas flows along the filaments, pooling at the nodes, forming galaxies and clusters. The structure is fractal-like, but not truly fractal, self-similar on certain scales, but smooth and uniform on the very largest. On scales above about 1 billion light-years, the universe is homogeneous, the same in every direction, the same density, the same temperature, the same composition. The cosmic microwave background confirms this. At the largest scales, the universe has no preferred location, no center, no edge, no special place. The principle of mediocrity applies not just to our planet or our star, but to our position in the cosmos. We are nowhere in particular, and everywhere is nowhere in particular. But within that grand uniformity there are pockets of extraordinary violence, objects so energetic that they defy easy comprehension. In 1963, an astronomer named Martin Schmidt at the Palomar Observatory was puzzling over the spectrum of a peculiar object called 3C273. It looked like a star, a single point of light, but its spectrum was bizarre, showing emission lines that did not correspond to any known element. Schmidt stared at the spectrum for weeks before realizing that the lines were, in fact, perfectly ordinary hydrogen lines, but redshifted by an enormous amount corresponding to a recession velocity of about 16% of the speed of light. If Hubble's law applied, this meant the object was about 2.4 billion light-years away. And if it was that far away and still appeared as bright as a 13th magnitude star, then it was emitting more energy than an entire galaxy, hundreds of times more energy than all the stars in the Milky Way combined, from a region of space no larger than the solar system. These objects were called quasars, quasi-stellar radio sources, and they were the most luminous things in the universe. It took years to understand what powered them. Supermassive black holes at the centers of distant galaxies, actively consuming matter at prodigious rates. As gas spirals into the black hole, it forms an accretion disk, a swirling, superheated platter of matter that reaches temperatures of millions of degrees and radiates energy with terrifying efficiency. The process converts matter to energy far more efficiently than nuclear fusion. Up to 40% of the rest mass of the infalling material can be radiated away, compared to less than 1% for hydrogen fusion in a star. Quasars are black holes in their most ravenous state, and they are visible across the entire observable universe, beacons of destruction that outshine everything around them. The most distant quasars now known exist at redshifts greater than 7, meaning we see them as they were when the universe was less than 800 million years old. They contain black holes of 1 billion solar masses or more, and their existence so early in cosmic history is deeply puzzling. How did black holes grow so large so quickly? Did they start from the collapse of ordinary massive stars and grow by accretion? Or did they form from entirely different processes? The direct collapse of enormous gas clouds, for instance, bypassing the stellar stage entirely? This question is one of the great unsolved problems in astrophysics, and the James Webb Space Telescope has found quasars and active galactic nuclei at even earlier epochs, pushing the mystery further back in time. There is another class of cosmic explosion that for a brief moment outshines everything else in the universe, and it was discovered entirely by accident, by satellites that were not looking at the sky for scientific purposes at all. In the late 1960s, the United States launched a series of military satellites called Vela, designed to detect the gamma-ray signature of nuclear weapons tests in violation of the Nuclear Test Ban Treaty. The satellites worked as designed. They detected gamma rays, but the gamma rays were not coming from Earth. They were coming from deep space, brief, intense bursts of gamma radiation lasting from fractions of a second to a few minutes, appearing from random directions and never repeating from the same location. The military data was declassified in 1973, and the astronomical community was baffled. Gamma-ray bursts, or GRBs, remained one of the deepest mysteries in astrophysics for the next quarter century. Their origins were unknown, their distances uncertain, and their energies, if they were extragalactic, were almost impossible to comprehend. The breakthrough came in 1997 when the Italian-Dutch satellite BepISAX detected a gamma-ray burst and, for the first time, identified an afterglow, a fading glow of X-ray and optical light at the position of the burst. Telescopes were pointed at the afterglow's location and found a faint galaxy at a cosmological distance. The burst was indeed extragalactic, and its energy output, assuming it radiated equally in all directions, was equivalent to the rest mass energy of an entire star converted to gamma rays in a matter of seconds. This was several orders of magnitude more energy than a supernova. The mystery deepened before it clarified, but eventually two distinct types of gamma-ray bursts emerged. Long-duration bursts lasting more than 2 seconds are associated with the deaths of extremely massive stars, hypernovae, the most violent supernovae, in which the core collapses to form a black hole and the infalling material launches relativistic jets that punch through the outer layers of the star and emit intense beamed radiation. Short-duration bursts, lasting less than 2 seconds, are associated with the mergers of compact objects, neutron stars crashing into each other or into black holes. The LIGO detection of a neutron star merger in 2017, accompanied by a short gamma-ray burst detected by Fermi within 2 seconds, provided direct proof of this connection. Gamma-ray bursts are the most energetic events in the universe since the Big Bang itself, and they occur at a rate of about 1 per day somewhere in the observable universe, brief flashes of annihilation that punctuate the cosmic darkness with fleeting, extraordinary violence. And yet, amid all this violence, the universe also builds. It constructs over billions of years structures of astonishing complexity and beauty. Consider the life cycle of a star like the Sun, which is itself a kind of slow-motion alchemy. Born from a collapsing cloud of gas and dust, the raw material left behind by previous generations of stars, a protostar forms at the center, growing denser and hotter as gravity pulls matter inward. When the core temperature reaches about 15 million degrees Celsius, hydrogen nuclei begin to fuse into helium, releasing energy that halts the collapse and establishes a balance, hydrostatic equilibrium that will last for billions of years. The star settles onto the main sequence, the long, stable phase of its life, shining steadily, converting about 600 million tons of hydrogen into helium every second, losing about 4 million tons of mass as energy in the process, energy that takes about 170,000 years to travel from the core to the surface as radiation, and then just 8 minutes and 20 seconds to cross the 150 million kilometers from the sun to your skin as sunlight. Our sun is about 4.6 billion years old, roughly halfway through its main sequence life. In about 5 billion years it will exhaust the hydrogen in its core and begin to change. The core will contract and heat up. The outer layers will expand enormously and the sun will swell into a red giant star hundreds of times its current diameter, large enough to engulf Mercury, Venus, and possibly Earth. The temperature at the Earth's surface, if there is still an Earth, will rise above 1,000 degrees. The oceans will boil away. The atmosphere will be stripped. Everything that exists on this planet, every forest, every city, every fossil, every work of art, every trace of every civilization that has ever existed, will be vaporized and absorbed into the outer envelope of a dying star. Eventually, the red giant will shed its outer layers in a gentle puff of glowing gas, a planetary nebula, a structure of haunting beauty visible through small telescopes, shells and rings and filaments of ionized gas illuminated by the hot core that remains. And that core, now exposed and slowly cooling, will become a white dwarf, a dense Earth-sized remnant, no longer generating energy, slowly radiating away its residual heat over billions of years, fading from white to yellow to red to infrared, and eventually, in the incomprehensibly distant future, to a cold, dark cinder, a black dwarf, a stellar corpse floating in the void. No black dwarfs exist yet. The universe is not old enough. The first ones will not appear for trillions of years, long after every star now shining has burned out. There is something simultaneously sobering and liberating about the long view of cosmic time. The universe is 13.8 billion years old. The sun has another 5 billion years. The last stars, small, cool red dwarfs burning their hydrogen with extraordinary miserliness, will continue to shine for trillions of years, perhaps 100 trillion, before they too exhaust their fuel and fade. After the last star dies, the universe will enter a long, dark era dominated by black holes, slowly evaporating through a quantum process called Hawking radiation, the theoretical prediction by Stephen Hawking that black holes are not perfectly black, but emit a faint thermal radiation due to quantum effects near the event horizon. A stellar mass black hole would take about 10 to the 67th power years to evaporate. A supermassive black hole about 10 to the 100th power years. These are numbers that have no analogue in human experience, numbers so large that they make the current age of the universe look like the first tick of a clock. And after the black holes evaporate, what remains is a universe of photons and elementary particles, drifting apart in an ever-expanding, ever-cooling void, approaching but never quite reaching absolute zero, stretching toward a state of maximum entropy, the heat death, the final equilibrium, the ultimate running down of all processes, all energy differences, all structure. This is the most likely fate of the universe, according to current physics. And it is, depending on your temperament, either the most depressing or the most clarifying thing you can know. It means that everything is temporary. Every galaxy, every star, every atom will eventually be dispersed. And it means that the fact that complexity and beauty and consciousness exist now, in this brief window of cosmic history, is not a given, but a gift, not a permanence, but a moment, and perhaps all the more precious for its impermanence. But we are not done with surprises from the last 100 years. There is one more discovery that sits at the very beginning of the timeline, so early that it makes the cosmic microwave background look recent, and it explains something so fundamental about the universe that without it, nothing else would make sense. In the 1970s and early 1980s, physicists noticed several puzzling features about the universe that the standard Big Bang theory could not easily explain. The universe was extraordinarily uniform on the largest scales. The cosmic microwave background was the same temperature in every direction to 1 part in 100,000. But regions of the sky on opposite sides were so far apart that in the standard Big Bang model, they could never have been in contact. Light had not had time to travel between them. There was no way for them to have exchanged heat, no mechanism by which they could have equalized their temperatures. And yet they were the same temperature. This was called the horizon problem. And it was deeply troubling. There was also the flatness problem. The geometry of the universe appeared to be flat, or very nearly so, and this required an extraordinarily precise tuning of the initial conditions. Even a tiny deviation from perfect flatness in the early universe would have been amplified over time, making the universe either collapse back on itself or expand so rapidly that no structures could form. The fact that the universe was still so close to flat after 13.8 billion years meant that its initial density had been fine-tuned to something like 1 part in 10 to the 60th power. This level of fine-tuning was suspicious. It demanded an explanation. The explanation came from a physicist named Alan Guth, who in 1979 proposed that in the very first moments after the Big Bang, during the first trillionth of a trillionth of a trillionth of a second, the universe underwent a brief, violent period of exponential expansion, increasing in size by a factor of at least 10 to the 26th power in a tiny fraction of a second. This is cosmic inflation, and it solves both problems elegantly. Before inflation, the universe was small enough that every part of it was in contact, able to equalize temperature. Inflation then stretched this small, uniform region to cosmic scales, like pulling a wrinkled balloon taut until it appears smooth. The flatness problem is solved because inflation drives the geometry toward flatness regardless of the initial conditions, just as inflating a balloon makes any small patch of its surface appear flat. Inflation also explains the origin of the tiny fluctuations in the CMB, the seeds of all cosmic structure. Quantum fluctuations, normally confined to subatomic scales, were stretched by inflation to cosmic dimensions, frozen into the fabric of space-time as variations in density that would later grow under gravity into galaxies and clusters and the entire cosmic web. The universe in this picture is a quantum fluctuation writ large, a microscopic ripple amplified by exponential expansion that became everything. The evidence for inflation is strong but indirect. The pattern of fluctuations in the CMB matches the predictions of inflationary models with impressive precision. A more direct confirmation would come from the detection of primordial gravitational waves, ripples in space-time generated by the inflationary expansion itself, imprinted as a specific pattern of polarization in the CMB called B-mode polarization. In 2014, a team using the BICEP 2 telescope at the South Pole announced the detection of this signal, generating enormous excitement. The excitement faded when it became clear that the signal was contaminated by dust in our own galaxy, and the detection could not be confirmed. The search continues with more sensitive instruments and more careful analysis of foreground contamination, and the detection of primordial gravitational waves, if it comes, would be one of the most significant discoveries in the history of physics, providing direct evidence of processes that occurred when the universe was younger than a billionth of a billionth of a billionth of a billionth of a second. And inflation, if it is correct, may imply something even more extraordinary. Some versions of the theory predict that inflation does not end everywhere at once. In some regions of the inflating space, inflation stops and a normal, slowly expanding universe like ours forms. But in other regions, inflation continues and those regions expand exponentially, and within them new regions stop inflating and form new universes, each with potentially different physical constants, different particle physics, different laws. This is the multiverse. Not science fiction, but a logical consequence of inflationary cosmology, a potentially infinite collection of universes, each one a bubble in an endlessly frothing sea of expanding space, most of them inaccessible, unobservable, separated from us by inflating regions that no signal can ever cross. Whether the multiverse is real or merely a mathematical possibility is a question that sits at the boundary between physics and philosophy. It cannot be tested by any experiment currently conceived. It may never be testable. Some physicists embrace it as the natural conclusion of well-tested theories. Others reject it as unfalsifiable and therefore unscientific. The debate is ongoing, vigorous, and unlikely to be resolved anytime soon. But the fact that serious physicists are even having this debate, that the evidence from the CMB and particle physics and cosmological observations has led to a framework in which the existence of other universes is a reasonable hypothesis, tells you something about how far astronomy has come in 100 years from a universe that contained one galaxy to a universe that may contain infinite universes, from certainty to wonder, from the known to the staggeringly beautifully unknown. There's another recent mystery that has emerged from the radio universe, and it is one that astronomers are still struggling to explain. In 2007, an astrophysicist named Duncan Lorimer, along with his student David Narkevich, was sifting through archival data from the Parkes Radio Telescope in Australia when they found something no one had seen before, a single extraordinary intense burst of radio waves lasting about 5 milliseconds that appeared to have come from a cosmological distance. 5 milliseconds, shorter than a blink. But in that 5 milliseconds, the burst released as much energy as the sun produces in an entire day, from billions of light years away. The signal was so unusual that for years many astronomers suspected it was an artifact, equipment malfunction, terrestrial interference, a glitch in the data. More bursts were found in the archival data, always single events, never repeating, and always showing a characteristic signature called dispersion, a smearing of the signal across frequencies caused by its passage through the diffuse electrons that fill intergalactic space. The amount of dispersion was consistent with enormous distances, ruling out local sources. These were called fast radio bursts, or FRBs, and they became one of the hottest and most puzzling topics in astrophysics. The breakthrough came in 2016, when a fast radio burst was detected that did something unprecedented. It repeated FRB 121102, as it was designated, produced multiple bursts from the same location, ruling out any cataclysmic, one-time event like a supernova or a neutron star merger. Whatever was producing these bursts was surviving the process and doing it again. The repeating nature allowed astronomers to pinpoint its location with precision, a small, distant galaxy about 3 billion light-years away, and to study it in detail. Since then, hundreds of fast radio bursts have been detected, thanks in large part to a new radio telescope in British Columbia called CHIM, the Canadian Hydrogen Intensity Mapping Experiment, which was designed to study dark energy, but turned out to be an extraordinarily effective FRB hunting machine, detecting dozens of bursts per day. Some repeat, most do not. Some come from distant galaxies. At least one came from within our own in 2020. A magnetar in the Milky Way produced a burst of radio waves that would have been detectable as an FRB from another galaxy, providing the first strong evidence that at least some fast radio bursts are produced by magnetars, neutron stars with extraordinarily powerful magnetic fields, 1,000 trillion times stronger than Earth. But whether magnetars explain all FRBs or only some, and what specific mechanism produces the bursts, and why some repeat and others do not, and what we can learn about the universe by using FRBs as probes of the intergalactic medium, all of these questions remain open. Fast radio bursts are less than 20 years old as a field of study, and they are evolving rapidly. They may turn out to be a powerful new tool for cosmology, using the dispersion of their signals to map the distribution of matter between galaxies and measure the expansion rate of the universe, or they may reveal new physics, or both. The expansion rate of the universe, incidentally, has become a source of one of the most heated debates in modern cosmology, and it involves a discrepancy that refuses to go away. Hubble's original measurement of the expansion rate, now called the Hubble constant, was wildly inaccurate, about 7 times too high, because his distance calibrations were off. Over the decades, the measurement was refined, and by the early 2000s, 2 independent methods were giving results that appeared to converge. One method, based on the CMB, measuring the properties of the early universe and extrapolating forward using the standard cosmological model, gave a value of about 67.4 kilometers per second per megaparsec. The other method, based on direct measurements of distances and recession velocities using Cepheid variables and type Ia supernovae, the cosmic distance ladder gave a value of about 73. These 2 numbers should agree, they do not. The discrepancy is about 8%, which might seem small, but both measurements are now so precise that the chance of the disagreement being due to random error is less than 1 in a million. This is called the Hubble tension, and it is either the most important clue about new physics beyond the standard cosmological model, or the most frustrating systematic error in the history of astronomy. If the tension is real, if the universe really does expand at different rates depending on how you measure it, then something fundamental is missing from our understanding. Dark energy might not be a cosmological constant, it might be changing over time. There might be new particles or forces that affected the early universe. The standard model of cosmology, which has been spectacularly successful for 2 decades, might need revision. The James Webb Space Telescope has been brought to bear on this problem, using its infrared sensitivity to measure Cepheid distances with greater precision and to calibrate the cosmic distance ladder more carefully. Early results have confirmed the higher value obtained from the distance ladder, deepening the tension rather than resolving it. This is both frustrating and exciting. Frustrating because a clear resolution would be satisfying. Exciting because the history of physics shows that when measurements disagree and neither measurement is wrong, something genuinely new is often lurking beneath the discrepancy. Let us zoom out one more time as far as the mind can reach and consider the observable universe as a whole. The observable universe is a sphere centered on you, on any observer, with a radius of about 46.5 billion light-years. This number is larger than the age of the universe might suggest, because the universe has been expanding while the light has been traveling. The most distant light we can see, the cosmic microwave background, was emitted 13.8 billion years ago. But the space between us and the point of emission has been stretching ever since, so that the current distance to that point is about 46.5 billion light-years. The total diameter of the observable universe is therefore about 93 billion light-years. Within this sphere there are approximately 2 trillion galaxies, 200 billion trillion stars, and an unknown but potentially enormous number of planets. The total mass of ordinary matter, protons, neutrons, electrons, the stuff that makes up everything you can see and touch, is about 10 to the 53rd kilograms. The total mass, including dark matter, is about 6 times that. The total energy, including dark energy, is such that the density of the universe is precisely the critical density, about 9.9 times 10 to the minus 27th kilograms per cubic meter, or roughly 6 protons per cubic meter of space. The universe is almost entirely empty. The vast distances between stars, between galaxies, between clusters of galaxies, are filled with an almost perfect vacuum, not truly empty, but so close to empty that it makes the best vacuums achievable in any laboratory on Earth look like a dense fog by comparison, and beyond the observable universe. We cannot see beyond it. By definition, Light from beyond the horizon has not had time to reach us, but there is no reason to think the universe ends at the boundary of our observations. Inflation suggests that the total universe is far larger than the observable universe, perhaps infinitely larger. We may be seeing only a tiny bubble within an inconceivably vaster whole, like a fish in a pond, who can see only a few meters in every direction and has no concept of the ocean. As we survey everything that the last century has revealed, a pattern emerges, not in the data exactly, but in the shape of the story itself. Again and again the universe has turned out to be larger, stranger, older, more violent, more creative, and more deeply interconnected than anyone imagined. Every comfortable assumption has been overturned. The Milky Way was not the universe was not static. Space and time had a beginning. Most of the universe is invisible. The expansion is accelerating. Planets are everywhere. Black holes are real. Space-time ripples. The atoms in your body were forged in the furnaces of dead stars and scattered by their explosions. And at each step, the discovery came not from armchair speculation, but from looking, from building instruments of ever greater sensitivity and pointing them at the sky with patience and curiosity and a willingness to be surprised. Henrietta Leavitt measuring the periods of variable stars on photographic plates, Hubble peering through the eyepiece of the 100-inch telescope, Penzias and Wilson scrubbing pigeon droppings from a radio antenna, Jocelyn Bell scanning miles of chart paper, Vera Rubin measuring the rotation curves of galaxies that no one else thought were interesting, Robert Williams staring at nothing for 10 days, the LIGO team spending decades building an instrument to measure a displacement smaller than a proton, the Event Horizon Telescope team linking observatories on 4 continents to photograph an object 55 million light-years away. The James Webb team folding a mirror like origami and unfolding it 1.5 million kilometers from Earth with zero room for error. Each of these stories is a story of human stubbornness, human ingenuity, and human willingness to be wrong. The greatest astronomers of the last century were not the ones who were right most often. They were the ones who asked the best questions, built the best instruments, and looked most carefully at what the universe was actually doing, especially when it was doing something no one expected. There is a photograph that captures this spirit better than any equation or data table. It was taken on February 14, 1990 by the Voyager 1 spacecraft at a distance of about 6 billion kilometers from Earth, beyond the orbit of Neptune on the very edge of the solar system. The spacecraft had completed its primary mission years earlier, flying past Jupiter and Saturn and sending back images of alien worlds that astonished a generation. But before it departed the solar system forever, the astronomer Carl Sagan persuaded NASA to turn the camera around and take one last picture of home. In the photograph, Earth appears as a tiny dot, less than a single pixel, suspended in a beam of scattered sunlight. A pale blue dot, as Sagan called it, barely distinguishable from the artifacts of the camera's optics. And yet on that dot, every human being who has ever lived was born and died, every war was fought, every symphony composed, every meal prepared, every breath drawn, every act of love and every act of cruelty, every person you have ever known or heard of existed on that mote of dust suspended in a sunbeam in the vast and indifferent dark. Sagan wrote about the photograph with an eloquence that has rarely been matched, and his words carry a weight that increases with time rather than diminishing. The pale blue dot is not just a photograph, it is a mirror. It shows us not just where we are, but what we are, a species capable of sending a machine 6 billion kilometers into space and then turning it around to take a picture of its own insignificance. A species that can measure the age of the universe, and the temperature of a star, and the wobble of a planet around a distant sun, and the chirp of 2 black holes colliding 1 billion light-years away, and yet still struggles to treat its own members with decency and care. A species that lives on a rock orbiting a middle-aged star in the suburbs of an ordinary galaxy, in a universe that is mostly dark, mostly empty, mostly unknown, and that has the audacity to look up and ask, what is all this? How did it get here? What does it mean? Are we alone? The last 100 years of astronomy have not answered all of these questions. They have answered some spectacularly, definitively, beautifully. They have reframed others in ways that make the questions sharper and the possible answers more astonishing. And they have raised new questions that no one a century ago could have imagined asking: what is dark matter? What is dark energy? How did supermassive black holes form so quickly? What produces fast radio bursts? Is there life on Europa, Enceladus, or any of the billions of rocky planets orbiting other stars? Is the Hubble tension a clue to new physics? Does the multiverse exist? These questions are not rhetorical. They are active research programs pursued by thousands of scientists with instruments of extraordinary power and sensitivity. The next decade will see the launch of new space telescopes, the construction of new gravitational wave detectors, the deployment of missions to the ocean moons of Jupiter and Saturn, the completion of enormous ground-based observatories with mirrors 30 meters across. The rate of discovery is not slowing down, it is accelerating, much like the universe itself. And if you are listening to this in the dark, perhaps drifting towards sleep, perhaps letting the words wash over you like the cosmic microwave background itself, a faint, persistent glow filling every direction. Consider this. The photons striking the back of your eye right now, allowing you to read or dimly perceive the screen in front of you, are a form of electromagnetic radiation, cousins of the photons that Penzias and Wilson detected in 1964. Cousins of the gamma rays from distant bursts, cousins of the radio waves from pulsars and fast radio bursts, and the faint glow of the cosmic microwave background. Light in all its forms is the thread that connects everything in the universe to everything else. It carries information across billions of light years and billions of years, and it is the medium through which the universe reveals itself to any being patient and clever enough to pay attention. The hydrogen in the water in your body was formed in the first 3 minutes after the Big Bang. The carbon in your DNA was fused in the core of a star that exploded before the sun was born. The calcium in your bones was scattered by a supernova. The iron in your blood was the last element that star could make. The gold in any ring you might be wearing was forged in the collision of two neutron stars, an event that also produced gravitational waves that rippled through the fabric of spacetime and, billions of years later, were detected by lasers bouncing between mirrors in a vacuum chamber in Louisiana. You are not separate from the universe. You are the universe arranged temporarily into a pattern that can contemplate itself. And the fact that this arrangement has in the last 100 years managed to figure out so much about its own origin and structure and fate is, in the end, the greatest discovery of all. The night sky is still there above whatever ceiling you are lying beneath. The same stars that Hubble observed from Mount Wilson, that Bell detected as pulses on chart paper, that the James Webb Space Telescope studies in infrared wavelengths invisible to human eyes. The light from some of those stars has been traveling for years, decades, centuries. Some of the stars you see no longer exist. They have already died, already exploded, already scattered their atoms into space, but their light is still arriving. A message from the past, a reminder that the universe is always older than it looks. Close your eyes and you can still see it. Not the individual stars, not the galaxies, not the cosmic web or the CMB or the event horizons of black holes, but the sense of it, the scale, the depth, the astonishing, improbable, temporary beauty of a universe that bothered to become complex enough to notice itself. The expansion continues, the stars burn, the dark matter holds the galaxies together, the dark energy pushes them apart, The photons travel, the gravitational waves ripple, the atoms cycle from star to planet to living thing and back again. And somewhere on a small blue dot, orbiting a small yellow star in the arm of a spiral galaxy that is itself just one of 2 trillion, a species that has existed for a fraction of a cosmic eye blink is looking up and measuring and wondering and slowly, painstakingly, astonishingly beginning to understand the universe does not owe us comprehensibility. Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. The laws of physics discovered by beings on one small planet apply everywhere in the cores of distant stars, in the accretion disks of black holes, in the first moments after the Big Bang in galaxies so far away that their light has been traveling for almost the entire age of the universe. The same gravity that holds you to your bed holds galaxies together. The same electromagnetism that carries signals to your phone carries the spectrum of a quasar across 3 billion light years. The same nuclear physics that powers the sun powers every star you can see and every star you cannot. The universe is one thing governed by one set of rules, and we have figured out enough of those rules to predict the behavior of matter and energy across scales that range from the subatomic to the cosmic, from fractions of a second to billions of years. This is not an obvious thing. There is no guarantee that the universe had to be this way. There is no logical requirement that the laws of physics be simple enough for a species of primates to discover them, or consistent enough across time and space to be worth discovering. The fact that they are, that the universe plays fair, that it follows rules, that those rules can be uncovered by careful observation and tested by experiment, is itself a mystery, perhaps the deepest mystery of all, and one that no amount of observation can fully resolve. But observation is what we have. Telescopes and spectrographs and interferometers and satellite detectors and photographic plates and chart recorders and cryogenic particle detectors, buried deep underground instruments of every kind, pointed in every direction, collecting every form of radiation and vibration the universe produces. And the people who build them and operate them and analyze their data and argue about the results and publish their findings and revise their theories and start again. The enterprise of astronomy, of science itself, is a collective act of attention, a sustained and deliberate effort to pay attention to what the universe is doing rather than what we assume it should be doing. And for 100 years, every time we have paid attention carefully enough, the universe has surprised us. It has shown us that we live in an expanding universe born from an inconceivably hot, dense state 13.8 billion years ago. It has shown us that the expansion is accelerating, driven by a force we cannot identify. It has shown us that most of the matter in the universe is invisible, detectable only through its gravitational effects. It has shown us that planets are common, that other solar systems look nothing like ours, that the conditions for life may be widespread. It has shown us that black holes are real, that space-time ripples, that neutron stars forge gold, that the atoms in our bodies are recycled stardust. It has shown us the cosmic web, the deep fields, the fast radio bursts, the pale blue dot. It has shown us the beginning of time and hinted at the end of everything. And it has shown us something else, something that no instrument can measure, but that every honest scientist feels: humility. The universe is under no obligation to make sense to us, and yet it does partially, imperfectly, provisionally. Every answer raises new questions, every discovery reveals new ignorance. The more we learn, the more we understand how much we do not know. The known universe is spectacular. The unknown universe is almost certainly more so. If you have stayed with these words this long, whether alert or drifting, whether fascinated or soothed, you have been holding in your mind a century of human effort to understand the place we live, 100 years of looking up, 100 years of asking the oldest question our species has ever asked: what is out there? The answer, it turns out, is everything, and we have only just begun to see it. The light keeps arriving from stars that have already died, from galaxies that are already too far away to reach, from the cosmic microwave background that has been traveling since the universe was 380,000 years old, from gravitational waves that rippled through space-time when two black holes merged 1 billion years ago. All of it arriving here at this moment, at this planet, at this species which has the extraordinary and perhaps temporary ability to notice. The universe is not silent. It has never been silent. It speaks in light and gravity and radio waves and gamma rays and neutrinos and gravitational waves. It has been speaking since the moment of its birth, broadcasting its story in every direction at once, encoding its history in every photon, every particle, every ripple in the fabric of space. And for the last 100 years, we have been learning to listen. The stars are still burning, the galaxies are still receding, the dark matter is still holding the cosmic web together, the dark energy is still pushing everything apart. And somewhere on a small, warm, wet planet orbiting a small yellow star, a species that has existed for the blink of a cosmic eye is looking up at the night sky and seeing, for the first time in its history, not just points of light, but the true face of the universe. It is older than we imagined. It is larger than we imagined. It is stranger than we imagined. And it is more beautiful than we imagined because it is real, and because we are part of it, and because we can know it, and because knowing it changes nothing about its indifference and everything about our place within it. The last 100 years have taught us that. The next 100 will teach us more. And whatever those discoveries are, whether they confirm what we suspect or shatter what we believe, they will come from the same source they have always come from. A human being pointing an instrument at the sky and paying very, very careful attention to what comes back. The night is quiet, the stars are out, the universe is doing what it has always done, expanding, cooling, building, destroying, creating the conditions for complexity and consciousness and wonder. And you, made of atoms forged in stars that died before the sun was born, made of matter that has been part of the universe since the beginning, are here, now, alive, aware and listening. That is, when you think about it, the most extraordinary discovery of all.